Good morning. Morning. Good morning. Samuel. Samuel Mokai, how are you? Sami. Dorlin. Nanzi Atieno. Esther. Faith Mtavia. Esther, how are you? Yusuf Mohammed. Melvin. Oma.
Yes.
Am I audible?
Yes, you're audible.
Good. So thanks for joining and coming to class with that short notice. So I hope you can also see my screen, my whiteboard. Able to see my whiteboard?
Yeah, the whiteboard is clearly visible.
Okay, good. Fine. We are going to discuss about the relations and functions. This is a key chapter that will help us to discuss relationships between sets and its elements, and then help us build foundation on how to start our second part of the course, calculus bit. So it's a connection between what we are studying on sets, and so therefore topic on sets forms the prerequisite to this chapter. So in summary, so introduction of the chapter. So we extend the concept of sets to include, I hope you can see what I'm writing. Are you able to see what I'm projecting and writing?
Yes.
Yeah, good. So we extend the concepts of sets to include concepts of relation and functions. So the relationship between elements of a set always occur in many contexts, and such relationships among elements of the set is what will help us to define a relation. And once we have defined a relation, we'll use it to define functions and see different kinds of functions and relations that are actually applicable in many fields, including finding or solving problems to determine cities linking different airlines. So that's an advanced application of relations. Also, we can use the concept of relations to create algorithms that store information in computer programs. So the topic or the concept of relations and functions is very broad in terms of applications. So begin by rediscussing about the Cartesian product. Which will help us to define a relation. So we remember that to define Cartesian product of two sets A and B, for any two sets A and B, the Cartesian product of A and B denoted by is defined as A cross B is a set of all paired elements A, B, such that the first element A comes from set A and the second element B comes from set B. So this is how we define Cartesian product. If you remember our discussion on sets, is one of the set operations that we did. So a binary relation, we can give the formal definition of a binary relation. So definition: for sets A and B, any subset of A cross B is called a binary relation from A to B. So any subset of the Cartesian product of set A and B is called a binary relation from set A to set B. Then any subset of a set crossed with itself is called a binary relation on the same set. So that's how we define a binary relation. So they just the subset of a Cartesian product of two sets or subsets of Cartesian product of a set by itself. then a binary relation from set A to set B is a set denoted by R of ordered pairs where the first element of each ordered pair comes from set A, and the second element comes from B. So we'll denote relations by this binary relations by this letter R, which is simply set of all ordered pairs of elements such that the first element in the pair comes from the first set A, and the second element from the pair comes from the set B. So let's give some examples here. So if I have set A with elements 2, 3, 4, and I have set B with elements 4 and 5, then the following are some relations from set A to set B. So I can have empty set is a subset of A cross B. So maybe probably, so empty set is a subset of A cross B. So it's a possible element or a possible relation from A to B. And then we can have a relation with just this one pair of elements 2, 4. We can have a relation 2, 4, and then 2, 5. I can have B A cross B. So please remember that from our earlier discussion on sets, we say that empty set and the set A are subsets of set A, i.e., for any set A, empty set is a subset of A, and A is a subset of itself. So that's why when we have been given set A with elements 2, 3, 4, set B with elements 4, 5. So if you are to define the Cartesian product of A and B, so what would be my first element in this Cartesian product? The pair will have which elements? Which element? The first pair in A cross B. Do you recall what we mean by Cartesian product of two sets? Do you remember what we mean by Cartesian product of two sets? So you can actually, the answer is either yes or no. So if you don't know, then I can remind you.
No.
Okay, so this is, so probably, so recall, we have already given that Cartesian product So we have let A and B be two sets. Then the Cartesian product of A and B, usually denoted by is a set of all ordered pairs such that this first number in the pair A comes from set A and the second number B comes from set B. So that's why I wrote that to write this one in set builder notation, we write A cross B is a set of all ordered pairs A, B, such that A is from set A and B is from set B. So when you need to understand the concept of Cartesian product so that actually the relations becomes easier for you to understand. So that's how we define Cartesian product. And so remember here, similarly, if I say B cross A, I'll have all ordered pairs B, A, such that B is from set B and A is from set A. So that is how we define the Cartesian product of two sets. So for example, if I give you A to be the set A, B, C, and B be the set 1, 2, say 3, then when I tell you to define A cross B, this is how you work them out. You take every element in set A, the first set, then you pair with all the elements of set B. So you do that for every element of A until you have all the pairs with the element in the second set. So I'll take A, pair with 1, take A, pair with 2, take A, pair with 3. And once you have paired the first element A with all the elements of B, you go to the next one, So we have B, comma 1, followed by B, comma 2, followed by B, comma 3. Then who can tell us the next element?
C, 1.
C, comma 1, followed by
C, 2.
C, comma 2, followed by
C, 3.
correct, C, comma 3. So that is how we define the Cartesian product of A and B. And then let's define B cross A. So B cross A means that the first element in every pair will be coming from set B. So the first one, you take 1, comma A, followed by
two.
So that you don't confuse yourself, just ensure that you take every element and pair with the element in the second set, all of them. So next one, you say 1, comma B, and then followed by 1, comma C. The next will be
2, comma A.
2, comma A, correct, followed by 2, comma
2, comma B.
Comma B, correct, followed by
2, comma C.
2, comma C. And then next 3 A,
3,
then
3, B,
3 B,
3, C.
3, comma C. And please, you remember when we were discussing about sets, be careful on what you're writing. Remember all the brackets, this kind of brackets, these curved brackets don't mean the same as square brackets, don't mean the same as curly brackets.
2,
So
B.
when we are writing the pairs of elements in the Cartesian product, we use these curved brackets. These are the brackets we use. So don't replace this curved bracket by either square bracket or these curly brackets, or they have totally different meaning. If you write A, comma B is different from writing A, comma B. And this is also different from writing A, comma B. So this is an element. This is an element in the Cartesian product, while this is a set when you write in this form. And this is actually a closed interval from A to B. So you have to be very, very careful on what you write. So when you are writing elements inside the Cartesian product, you use these curved brackets. So don't replace by these other brackets because it will totally have a different interpretation. Now, from this result, is an element A, comma 1 the same as element 1, comma A? Are those two the same? And to know, okay, to know whether they are the same or not, just remember, like if someone asks you, plot the point, say A is a point 2, comma 1, and B the point 1, comma 2. Are they at the same location or they are different? If you are to plot in the Cartesian plane, 2, 1 and 1, 2, are they the same point?
No.
They aren't.
No.
Because if you
No.
are to put this one in the Cartesian plane, say this is 1, this is 2, this is 3, 1, 2, 3. So remember the first number is always the X value, second number is the Y value. So this 2, 1 means X is 2, Y is 1. So I'll have this point here. And then 1, 2 means X is 1, Y is 2. So I'll have this point here. So this way I'll have B. So 1, comma 2 is not the same as 2, comma 1. So therefore the element A, comma 1 and element 1, comma A, they are not equal. So these two are never the same. So then you can't say that A cross B is not equal to B cross A. So those two sets are not equal, but they are equivalent. Equivalent means they have the same cardinality. So A cross B cardinality the same as B cross A cardinality, but the two sets are not equal. They're equivalent but not equal. And if I say 1, A, and someone has A, 1, is this equality a true equality or is not true? Is this equality correct, true or
Yes.
is false?
True.
This one is true. This is correct because remember these are set and this also a set. So you can clearly see that the way you write your brackets really can actually give a different interpretation. That A1A and A1 written in this form, they are the same because these are just sets. But 1, A and A, 1 written as pairs of cross product or they are not the same elements. So that one should be very clear. So then having understood the concept of the Cartesian product, now we should be able now to understand what I was asking here. That we have this set A. Okay, maybe now, can we now list the elements of A cross B in this case? What will be my first element?
2,4.
2,4, correct? Followed by?
True.
2,5.
2,5, followed by?
3,4.
3,4, followed by?
3,5.
3,5, followed by? Next one?
4,4.
4,4, and then?
4,5.
4,5. So please, someone wanted to skip 4,4. Please note that the way we are doing this Cartesian product is exactly the same way you see points in the Cartesian plane. So remember 4,4 is a point, which means that X value is 4, Y value is 4. So you don't skip it, you just write it, follow the same pattern on how you are writing the elements of the Cartesian product. So because you are picking every element of the first set, then you pair with all other elements of the second set. So this is what we have as our A cross B. So remember a set is a subset of itself, and we are saying that a relation is simply a subset of the Cartesian product of two sets A and B. So that's why we are saying that if this is my set A and this is my set B, then these are possible relations. These are not the only relations, but these are possible relations because empty set is a subset of this set. So that's why we are having this one as one example of a relation on A cross B, or a relation from A to B. And then you see that 2,4 is an element in this set. And you actually, when you use that element to form a set, then that will be a subset within this set A cross B. So this is also a possible relation on A cross B. And then here you see elements 2, 4, and 2, 5 are within this set A cross B. So when you combine them, then they also form a smaller set within the A cross B set. So that's a possible relation also on A cross B. And then also we know that a set is a subset of itself. And since a relation from A to B is simply subset of A cross B, then we can actually pick the whole set itself to also form another relation. Can you also give me some of other relations that we can also get from the same problem? Apart from these four, which other relations can also be formed from A cross B?
3,4, 3,5.
3, 4, 3, 5. Correct. So these are two elements within A cross B, and when you use them to form a set, then we are sure that that set actually is a subset of this bigger set A cross B. So this is also another possibility. Any other?
4,4, 4,5.
Yes, 4,4 and 4,5. When you use them to form a set, then it can also be regarded as an example of a relation from set A to B. Any other? Okay, maybe for us to get this one clearly, you remember when we were discussing about sets, we defined power set. What is power set of a set A?
Sets of A.
Means? So if I have let A be a set, then the power set of A denoted by is
All subsets of A.
correct. All subset, the set is a set of all subsets of A. So maybe we can remind ourselves how actually we get this one clear. Remember, the concept of relation is actually a very easy concept to understand. If you understand what you mean by power set and then you understand what you mean by Cartesian product, it'll be very easy for you to understand most of the terminologies here. So for example, if I have a set, say A, with elements A, B. So what elements forms the power set of A? Remember, the first thing is just start with the empty set, and then another possible subset. If you have only two elements, set formed by
A.
A alone. Any other?
B.
Set formed by B alone.
B.
And then the other one?
B.
A comma B itself. Okay. Yeah. Set formed by all the elements now within A, which is actually the same set as A. Correct. And if I have a set B with elements 1, 2, 3, let's form the power set of B. So the first element in this power set will be
An empty set.
empty set which has 0 elements, and then the other subsets,
One.
a set formed by 1 alone. Any other?
Followed formed by
Formed
2.
by 2,
By 3.
followed by 3. So we have exhausted all the possible subsets that can be formed by 1 element each. And then from 1 element, we got 2 elements, which
1 and 2.
1 and 2, correct? Any other?
1 and
2 and 3.
2 and 3. Any other?
3 and 1.
1 and 3.
1
1
and
and
3.
3. So 3 and 1 and 1 and 3 are the same thing, okay? Because we say that when you're writing elements of a set, order does not matter. So 1, 3, and 3, 1 mean the same thing. And then finally, the whole set itself, okay? Yeah. So this is the same concept that we are using there now. When we say a relation from set A to B, we mean any subset of the Cartesian product of A and B. So then there are many relations that can be defined on any two sets or even on a set by itself. So note, we use the notation. We write A, R, then write B to denote that element A, comma B is in relation R. So when A, comma B is in R, A is said to be related to B by R. So maybe also for us to get a better understanding of relation before we start discussing different types of relations, consider this. So let A be the set of cities and B be the set of East African countries. Define a relation R by specifying that A, comma B belongs to R if city A is in country B. So can you give me so what are the East African countries? Maybe for us to be more specific, if we say maybe capital cities, maybe can say maybe capital cities, just to have them, few of them. So let A be the set of capital cities and B be the set of East African countries. Define a relation R specifying that A, comma B belongs to R if city A is in country B. So what countries forms East African forms East Africa?
East Africa.
So maybe we can list the elements of set A and let's list elements of set B. So B are countries. So which countries are in East Africa?
Tanzania,
Kenya, Tanzania, Ethiopia, Uganda, Rwanda, Somalia,
Kenya,
Djibouti, Burundi,
Uganda,
Rwanda, Djibouti.
Okay, we are not sure, so I'm not sure whether those are the only ones or there are still many other. Assuming this is how we want to define our B, and what are the respective, what are the capital cities for these countries? You can say
Dodoma.
capital city of Tanzania is
Dodoma.
Dodoma. Kenya is Nairobi. Uganda,
Kampala,
and then Rwanda, Kigali. So can you tell me how R will look like? What the first element of R? Remember, the elements of R are A, comma B, where A is a capital city and B is its respective country.
Dodoma, Tanzania.
Dodoma, Tanzania, correct? comma Tanzania. Okay, from the framing of the question, can we have an element like Dodoma, Kenya?
No.
No, because now Dodoma is not found in Kenya, correct? Then the other element,
Nairobi,
Okay.
Kenya.
Nairobi, Kenya. The other one,
Uganda.
Kampala, Uganda. And finally,
Kigali, Rwanda.
Kigali, Rwanda, correct. Kigali, Rwanda. So when the question is more specific, then actually it can narrow down to have just a specific relation from two sets. But when it's open, then there are many relations that can be defined. But when you go into nitty-gritty detail, then you'll be able to reduce the possibilities of the relation that can be formed. So example 3. So let A be the set 0, 1, 2, and B be the set A, comma B. Then we can have a relation R from A to B as 0, 1, 0A, 0B. Next element will be maybe at least also we can also have 1, comma A. We can have, okay, so there are many relations that can be defined if you are not specific on how we want to do the pairing. So for example, if I stop at 2, comma B, this is an example of a relation because relations are just subsets of the Cartesian product. So you don't have to list all the elements of the Cartesian product. It's a relation from A to B. So this means, for instance, that 0 is related to A by this relation R. We can say 1 is related to A by relation R. We can say 2 is related to B by relation R, etc. So just to explain how we can say that when you write A, comma B, then you can write it as A, R, B. So that is how we understand the concept of relations. Then a relation on a set A is a relation from the set A to the set A itself. So a relation from A to A is simply a relation on set A. So for example, if we let A to be the set with elements 1, 2, 3, 4, what which ordered pairs are in the relation R such that the elements of this relation are A, comma B, and A divides B. I want you to write for me the elements of that relation R. So I give you 2 minutes to do that. Write all the elements of R. with that instruction. So let's see this. So that one way of doing this problem is to sketch. So let this be set A, and then we are moving from A to A itself. So then I just is still just A. So A has elements 1, 2, 3, 4. So this being the same LS set, we have yes. Isn't it? So then now we have this is 1, 2, 3, 4. 1, 2, 3, 4. So remember the instruction is that we have our elements as A, comma B, where A divides B. Okay, can 1 divide 1?
Yes.
Yeah, so then we have 1 can be taken to 1. Can 1 divide 2?
Yes.
Yes, 1 divide 2. So can 1 divide 3?
Yes.
So 1 divides 3. So have an arrow from 1 to 3. Can 1 divide 4?
Yes.
Yes, so 1 divides 4. So we have 1, 1, 1, 2, 1, 3, 1, 4 will be elements of set elements of relation R. And then let's see, can 2 divide 1?
No.
So divide simply means that you don't have a remainder when you do the division. So 2 cannot divide 1. So we don't have an arrow from 2 to 1. Can 2 divide 2?
Yes.
Yeah, so you draw an arrow from 2 going to 1. Can 2 divide 3?
No.
2 cannot divide 3. Then can 2 divide 4?
Yes.
Yes.
Yes. So you draw an arrow from 2, will be paired with 4. Good. Then we go to element 3. Can 3 divide 1?
No.
Can 3 divide 2?
No.
Can 3
No.
divide 3?
Yes.
Yes.
Yes. So then you draw an arrow from 3 to 3. So I'll have element 3, 3. Can 3 divide 4?
No.
It can't. So that'll be the only pair from 3. And then lastly, can 4 divide 1?
No.
Can 4 divide 2?
No.
Can 4 divide 3?
No.
Can 4 divide 4?
Yeah.
Yes.
Yes.
So then you draw an arrow from 4 going to this other 4. Good. So therefore, with that graph or graphical representation of what the instruction of the condition in the relation tells you, then you can comfortably write all the elements of R. So 1 is paired by all the other elements in the same set A. So we'll have 1, 1, 1, 2, 1, 3, 1, 4, and then 2 is paired by 2 with the condition. 2 is paired by 3. 2 is paired by 4 with that same condition. And lastly, second last, 3 is paired with 3. And then 4 is paired with 4. So this is how the relation R will be defined. Maybe let's call it R1. Let's give it the name R1. That the instruction for R1 is elements are A, B, where A divides B. What if we have R2 such that R2 has elements A, B, A is less than B. Are you able to tell the elements of R2, how they look like? With the instruction A is less than B. So just the easiest way is just to draw, you can actually draw the two sets and then start relating. So then R2. So what would be the first element? That the first number must be less than the second number.
1,2.
1, 2.
1,3.
1, 3.
1, 4.
1, 4. The next?
2,
2, 3.
2, 3.
2, 3.
2, 4.
2, 4, correct.
3, 4.
3, 4. Is there any other?
No.
There isn't. Good. So that is will be our R3. And then let's have R2. R3 to be this relation with elements A, B, such that A is equal to B. Can you be trusted with the listing elements of this relation if you are on the same set A?
1,1.
1, 1.
2, 2.
2, 2.
3, 3.
3, 3.
4, 4.
4, 4. Good. And then if we have a relation R4 with the condition, it has elements A, B, such that A is greater than B.
2, 1.
So can we list all the elements of R4.
2, 1,
2, 1,
3, 2,
3, 2,
4, 3,
4, 1.
4, 1. So if you can be orderly, then it'd be easier for you not to make any mistakes. So can we? So the best way, if you are orderly, you not make mistakes. So let's try to be orderly so that we take care of all the things. We don't leave out anything. So 2, starting with 2 will only have that element. Then if we start with 3, we have 3, 1. Then
3, 2,
3, 2. Then next will be
4, 1,
4, 1,
4, 2,
4, 2,
4, 3.
4, 3. These are very serious class. Good. So that is how we understand from the property, you can always list the elements of the relation. So lastly, properties. Some call properties, some call types of relations. So there are several properties that can be used to classify relations on a set. So the first one is what we call reflexive relation. So we'll define and give an example in each case. So a relation R on a set A is said to be reflexive a relation R on a set A is said to be reflexive if for all elements X in A, X, X must always be in R. So a relation R is said to be reflexive if elements X, X are in R for all X in the set A. So I'll give an example, and then I'll give two relations, and I want you to tell me whether they are reflexive or not. So example, let A be the set with elements 1, 2, 3, 4. And R1 with the relation 1, 1, 1, 2, 1, 4, 2, 3, 2, 2, 3, 3. And then R2 be the relation 1, 1, 2, 2, 3, 3. R3 be the relation 1, 1, 1, 2, 2, 2, 3, 3, 4, 4, 4, 1. And then R4 be 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 3, 3, 4, 4, 1, and 4, 4. So which of these relations are or is reflexive? I want to give you 1 minute or 2 minutes. Write them, and then from the definition, I want us to discuss which of these relations So which one is reflex? Just put on top there. Look at you.
R3 and R4.
So which relation is reflexive from the definition? Is R1 okay? Let's go one by one. Is R1 reflexive?
No.
Yes or no?
No,
Why?
because it lacks 4, 4.
4 is lacking. Okay.
Ah,
Yeah. So this one is not correct. This one is not reflexive because element 4 is not there. Put that. Okay. And then R2.
no.
No, with the same reason. Okay.
Yes.
Yeah. So this is also not reflexive because remember the definition is that for all elements x, then x comma x must be in R. So when A has 1, 2, 3, 4, so every element should be paired by itself, all the elements of set A. So then that's why we are ruling out R2. And then R3.
Yes.
R3 is reflexive because we can see 1, 1, we can see 2, 2, we can see 3, 3, we can see 4, 4. We don't care if there's extra things, provided all those elements are there, then it qualifies to be called reflexive. Correct. And then R4
Yes.
Yes.
is also reflexive because we can see 1, 1, we can see 2, 2, we can see 3, 3, and we can see 4, 4. So that's what we have, or what we mean by reflexive. And then the other type of relation is what we call the symmetric. So a relation R on a set A is said to be reflexive.
Symmetric.
To be symmetric, yes. Symmetric if x comma y in the relation implies y comma x is in the same relation for any x, y in A. So a relation R on a set A is said to be symmetric if you see an element x comma y in R, then it must also have an element y comma x for all elements x, y taken from set A. Let me also define another type of relation before we give an example. Then antisymmetric. So a relation R on a set A is said to be antisymmetric if an element x comma y in the relation R and an element y comma x in the relation R implies that x equals to y for all x and y in A. And what you must always remember, note that the term symmetric and antisymmetric are not opposites. since a relation can have both of these properties. Or may lack both. So just like that, and then I give the two more definitions, then we give an example that can help us to understand or master all the terms. So transitive, so a relation R on a set A is said to be transitive if whenever an element X, Y is in R and YZ is also in this set, in this relation R, then XZ must also be in this relation R for all X, Y, Z in A. So if we have an element X, Y and Y, Z in R, then you need to have an XZ in R for all the elements X, Y, Z picked from A. This is what we call equivalence relation. So equivalence relation is a relation that has the three properties: reflexive, symmetric, and transitive. So a relation R on a set A is said to be an equivalence relation if it is reflexive, symmetric, and transitive. And lastly, so a relation R is said to be a partial order or simply a partial ordering if it is reflexive and symmetric and transitive. So tell me when you are ready so that I give, in 5 minutes time, we give a few examples to help us understand these terms. So example. So consider the set A with elements 1, 2, 3. Let's have a set with 3 elements, 1, 2, 3. Then consider this relation R1 from A to A with elements 1, 2, 2, 1, 1, 3, and 3, 1. So can we say that this relation R1 is reflexive?
No.
No.
So so we can say R1 is not reflexive. R1 is not reflexive. What is the reason? Since
There is no one. It's not 2, 2, it's not 3, 3.
what makes R1 not to be reflexive?
1, 2, 2.
1, 1, 2, 2, and 3, 3 are lacking, okay?
Yes.
Yeah, so since 1, 1, 2, 2, and 3, 3 are not in R1. Good, because you say that for a relation R to be reflexive, then it should have elements x, x for all x in A. And since A has 1, 2, 3, then 1, 1, 2, 2, 3, 3 must be in a relation for it to be called reflexive. So those are lacking, so therefore R1 is not reflexive. Then can we say that R1 is symmetric?
Yes.
So R1 is symmetric
Yes.
since if XY
X, Y,
is in R1,
1, then Y, X.
then
Y,
YX
is in
is
R1.
in R1. For example, you are saying here we can see an element 1, 2. Also, we have 2, 1. So that when you switch the role, the first becomes the second, second becomes the first. We can see it. And then we can also have, we see an element 1, 3, and also we have element 3, 1. And because so those changing the order of the starting element and the ending element. Any element you pick in that R1, you must always find another element with all the elements switched. First becomes second and second become first. Then R1 is symmetric. Now, can we say that R1 is antisymmetric? Is it antisymmetric or not antisymmetric?
No, it's not antisymmetric.
What makes it not be antisymmetric? So this one is not antisymmetric. What makes it not to be antisymmetric? How did we define antisymmetric relations?
No. Maureen, the power.
Is equal to y.
Yeah, so remember, antisymmetric say that if element x comma y is in R and y comma x is in R, then it implies that the two elements must be the same, which is actually not true. One is not the same as
X
two. And
is not equal to y in any of
yeah. But then maybe let me just pause so that we can understand the interpretation of this one. If we have R2 to be the element, to be the set with elements A, comma B, such that A divides B. Can we define R2 from this set? A. What are the elements of R2?
1, 1.
1, 1.
1, 1, 2.
1, 2.
1, 3.
1, 3.
2, 2.
2, 2.
3, 3.
3, 3. Is there any other?
No.
No. So this from set A, this is what we define as our R2. So is this R2 reflexive?
Yes, it's reflexive.
Yeah.
It's reflexive, correct. So we can say R2 is reflexive because we can see all the elements 1, 1, 2, 2, and 3, 3, okay?
Mm.
And then is it symmetric? Is or is not?
It's not.
It's not.
It's not. E.g., 1, 2 is in R2, but 2, 1
Is not.
is not in R2. So that's how the reason you can actually give. Because we expect that when you see 1, 2, then you must see the opposite when you change the order. That's the interpretation. That's the definition of okay, it's not symmetric. That's how we define asymmetric. That when you see x comma y in R, then y comma x must be in the same relation. But that's not the case here. Now, can we say that R2 is antisymmetric?
Yes, it's antisymmetric.
Yeah, R2 is antisymmetric. What is the reason?
X is equals to y for all x, comma y, elements of A.
Yeah, so this is because for any two elements, A and B, such that A divides B and B divides A, then A must be the same as B. So remember the definition of arithmetic is that if you have an element A comma X comma Y, and you have Y comma X in the same relation, then that is only possible when the two elements are equal. And that is true. That you see one comma, or if this is your first A, this is your B, then when you change BA, we'll actually get the same numbers from the first position and the second position. So that is only possible when A and B are equal. So R2 is an example. R2 is an example of an arithmetic relation. So therefore, now you can. Okay, before maybe R3, let's have R3. If I have 1, 1, 2, 2, 3, 3, and I have 2, 3. Is R3 reflexive?
Yes.
R3 is reflexive, correct. So R3 is reflexive. And then is R3 symmetric?
No.
R3, what make it not be reflexive, not to be symmetric?
For XY, which is in R,
Yes.
there's no
YX
YX is not in R.
So just so now when they ask for a reason, actually just get a specific element that actually can make that definition not to hold. That's enough. A specific element that either maybe is lacking in R3 that makes it not conform to the definition of symmetric.
We have 2, 3, but not 3, 2.
Correct. Yeah. So R3 is not symmetric since an element 2, 3 is in this relation R3, but we can't see 3, 2 in R3. Remember the definition of symmetric was that if you see an X, Y in the relation R, then it must also lead you to an element Y, X. And you see we are seeing a 2, 3, but we can't see a 3, 2. So that's what makes it not to be symmetric. Then if I have a set A with elements 1, 2, 3, 4, this is the last one. I'm stopping. And I have a relation R1 on this set given by 1, 1, 2, 3, 3, 4, and 2, 4. Can I say that this relation R1 is transitive? Do R1 qualify to be called a transitive relation on set A?
Yes.
What makes that to be the case? So it's true that R1 is transitive. Since
We have 2, 3, 3, 4, and 2, 4.
yes. So remember the definition of transitive was that a relation R on a set A is said to be transitive if whenever. So remember the keyword there was if whenever. If whenever. That you see X comma Y is in R and you see Y comma Z is in R, then this leads you to having the first X related to the last Z here. X comma Z must be in the same relation R. So know that what you have to check for in a relation for it to be transitive is that check to see that there are two numbers which are related, X, Y, and then the second number from that is related to another different number, Z. So then it tells you that for those two pairs, where the last number in the first pair is the first number in the second pair, then your original first number in the first pair must be related to the second number in the second pair. So you see, we have 2 is related to 3, and then we go further, 3 is related to 4. So this correspondence of the last number in the first pair and the first number in the second pair leads you to taking now the first number in the first pair to be paired with the second number in the second pair. And then we can actually clearly see that we can see a 2, 4 here. So since 2, 3 is in R1 and 3, 4 is in R1 and we have 2, 4 being in R1. So that's what makes R1 to be transitive. That when you see an element which is actually in two different pairs, in the first pair is the second pair the first one. So those two pairs, the first element from the first pair should be paired with the second element in the second pair. If that's the case, then qualifies to be called transitive. So from the textbook I shared, get more of the examples and work out on them. So as an exercise, this is just continuation of your bookwork. So define domain and range of a relation. I'll prepare some few problems that actually you can work either in groups or alone to help you to master that. It's not an assignment. It's not work to be submitted, but just to help you discuss on relations. So next time we meet, we'll be discussing about functions, which will be on Friday, not tomorrow. So have a good day.
Same.
Okay, good. Actually, I've marked your assignment, all your assignment, but I'm still yet to record. The class is too big. I'm also having another class in economics with around 300 students. So marking is done, but I've not recorded. So I'll be requiring some assistance from some of you, those who are willing, so that you can the marks can be recorded and then the slips are given out. But I'm very happy with the way people are performing and the way they are doing the assignments. The trajectory is very good. So keep it up.